All right. So hello and welcome to our showcase on vehicle analytics from the ISL lab. So this is something we've been working very hard on for the last few months, and I'd love to show it to you today. So my name's Mustavi, and I'm the team leader for this project, which originally started as our senior project 2. I just graduated from IT, and I'm currently working as a full-time AI engineer at a startup here. And I will be the presenter for today, basically. And you can find me at my Twitter handle at Mustavi. So this is the agenda for today. So first we'll be talking about what is vehicle analytics and who this is for. Then we'll go in detail about the technologies vehicle analytics uses to make everything work together. Then I will give you a demo of the user interface and how we are able to show data live using a real-time database. Then finally, we will talk about some of our final thoughts on the project and show you some results of the training. So let's talk about this project and what it is all about. But before we get started, let me tell you a little story I find very interesting. I would like to go back 30 years in history. Before the days of Microsoft, back in 1975, Bill Gates and his friend Paul Allen opened up a company called Trafodata, where they used a computer to process raw data from roadside traffic counters and created reports for the engineers. However, unfortunately for them, the company a success because they were limited by the technology of their time. Now coming back to 2020, technology has come quite a long way since 1975. Now we have more powerful computers capable of parallel processing, giving us the ability to do things that was never before possible, like object detection and just by using cameras. So this is where vehicle analytics comes in. Using the latest deep neural network technologies, we detect, classify, track, and count vehicles and process all raw vehicle data to show on a beautiful dashboard in real time. So now that you have an idea of what vehicle analytics is, let's talk a bit about who this is actually for and the origins of this project. So vehicle analytics was originally commissioned by Stadium 1, a shopping center in Bangkok. Their team wanted to know the traffic density around their premises, and they wanted to know the analytics of the cars being parked in their parking lots. And we actually showed them a working demo of vehicle analytics, I think a few months ago, and they loved it. Another potential customer for this can be the roads and highways departments of governments around the world who may wish to perform traffic surveys for a particular road or many roads. So now that you have an idea of what vehicle analytics is and who it's for, let's talk a little bit about the platform itself and how it works. Here's an overview of the platform here. So we have live access to the Stadium 1 cameras, and we read the video using our video capture module. Then it passes through our detection and classification module, which is powered by a deep convolutional neural network. And it returns us the locations of the vehicles and the types of the vehicles on the road. Then the tracking module uses the detection data to track the vehicle's movement on the road, which we later use for counting, basically. Here's a quick overview of the system architecture. The system comprises of various servers working in unison to provide, process the live data and in real time. And we have our own on-premise server, which runs the vehicle analytics client, and it does the initial data processing. Then they are uploaded to the cloud in Firebase and DynamoDB. Then the data is processed again on an EC2 instance on AWS Cloud, and it is sent directly to the web host. So now let's talk about how we do the detection and the classification of the vehicles. So like I said earlier, we are using a neural network to detect and classify the vehicles. So there are basically two parts to this. We have the training part, and then where we have the inference part, where we actually use the neural network model to detect vehicles. So here we will we will be talking about the training. So initially we tested various pre-trained models using the TensorFlow library, both version 1 and 2. While they tracked great at certain angles, for our use case and camera angle, the detection was not that great. So we decided to do transfer learning, where we basically teach the pre-trained model to detect better. We found that the faster RCN and Resonant 50 model performed the best for our particular use case. With a detection speed of 89 milliseconds and the mean average precision of 30, the Resonant 50 works perfectly in our case. But please note that a higher precision usually ends up in better detection, but it will also mean that your model will be a little bit slow. So in order to train our model to track vehicles better, we extracted the frames from the videos we recorded, and we labeled and pre-processed over 19,752 vehicle images over the span of 2 weeks. Training was done based on the Resonant 50 architecture, and it works so well because it's a bit different from the traditional stacked layer architecture where we have layers stacked over other layers separated by activation functions like ReLU or sigmoid. However, the limitations with the traditional models is that as the gradient of the loss function approaches 0, it makes the model harder to train. So the advantage of the Resonant architecture is that in order to mitigate the gradient loss issue, the input is added right before the convolution layer, right before the gradient reaches 0, resulting in a deeper neural network. And since we are classifying multiple objects, the Resonant 50 was great for inference in our use case. Let's talk a little bit about how we track vehicles in the frame. So a Kalman filter is used to track the vehicles, and it works by making an initial prediction of the next bounding box location. Then on the next frame, it takes in the measurements from the predictions and corrects it. So there are basically 3 steps. Now let's talk about vehicle counting. Vehicle counting is done by drawing a single line across the screen where we pick a region of interest. Every time the centroid of a bounding box passes through the line, we count it as one vehicle. Certain fail-safe measures are also there in place. For example, in the case where a vehicle is waiting on the region of interest line during traffic, we make sure not to count that vehicle as vehicles like passing by, or we don't register that vehicle. We also track parking slots at the Stadium 1 using one of their cameras. As you can see from the 2 dots here, when a car is parked in the parking spot, it turns red, and the system immediately starts sending data to the cloud in real time. If the intersection over union between the 2 bounding boxes of the detection and the parking spot match, we use the Hungarian algorithm to assign the detection to the parking spot. So now I'm going to give you a demo of the AI and how it works. So here you can see that as soon as the car is detected in our region of interest, it automatically updates on our UI dashboard in real time. And here's a video of our counting module where you will see the vehicles, as the vehicles pass through the region of interest line, we count that as we register the count for the vehicle. And you can also see that the vehicles are classified by the system as their respective types. So I'm going to give you a demo of the user interface now. Give me a second. Yeah, all right. So, okay. Let's go over the UI dashboard a little bit. You have this beautiful interface here. Some of the data here updates hourly, some of the in real time. So let's go through some of the data here. So on the card here, on this card here, you'll see today's overall data, including the number of vehicles that pass by today, and the peak and the least traffic flow. And along with the number of total parking spots for the day, and along with the average parking time. And here you can see the real-time data basically. So right now there's one car parked in the parking slot here, and this data is updated real time. If another car comes in, and this will be updated in real time basically. And these data is also, the parking data is updated real time, but the vehicle counting data and the traffic density data is updated hourly, on an hourly basis. Here we have the time series data and a comparison between yesterday's traffic time series and today's the time series data of today's data, today's traffic basically. And here's the weekly traffic density basically. So like on on previous days, on Mondays, how many total vehicles passed by, Tuesday, to how many total vehicles passed by. And finally, now we separate the total vehicle count by their class. For example, we have for this week, around 59,000 bikes passed by the road and 82,000 cars passed by the road, and the number of trucks that pass by the road and the number of buses that pass by the road. This is for the entire week, basically. And these are the categories. These are the category count by the day, basically. We have today's data, basically. Based on today's data so far, because today haven't ended yet. So today's data is basically, so far we got 7,168 cars and the 6,141 bikes. So this is basically by day, and this is the total weekly data. Okay, that is it for our UI demo. Okay. So now that you have an idea of how the platform works, let's talk a little bit about the results of our training. So here are the counting results compared to the pre-trained model. As you can see that the counting has improved significantly after we trained the model, as the bounding box centroids are detected and tracked properly, and now it's closer to the ground truth values. So to conclude our presentation, we talked about the inception of vehicle analytics and its use cases. We talked about its powerful capabilities, like using AI to detect and classify vehicles. And finally, we showed you a live demo of the app itself and how we track the vehicles in real time. While a lot of these techniques existed individually by themselves in the past, we made them work together in harmony to accomplish our goals for counting vehicles for analytics. We believe with further development, this project has the potential to be the standard for traffic monitoring everywhere. So this marks the end of our presentation today. I would like to thank my entire team at ISL for doing an amazing job, and especially Achantap for giving us the opportunity to work on this great project. So now we are open for questions if you have any. Thank you very much.
Okay, thank you very much, Mustavi. Okay, we got a raised hand here. Okay, Ken, you got a question?
Yes, I have a question about the car counting, like vehicle counting.
Yeah.
Like if you draw the line like that from this angle, will like when two vehicles like moving parallel, will they block each other and you cannot count the other one behind the previous one?
We haven't seen that case happen yet because of the camera angle is placed in a way that doesn't occur. But in the case where the vehicle is larger than the vehicle that is passing by from the other side, yeah, it blocks the detection and we don't register as a count. So this was actually, this was originally designed just as a proof of concept, right? So in a deployed situation, what we would do is we would, the camera angle would be obviously different, not this camera angle. But in the real world situation, we might mask out the other, the other lane basically. So it doesn't affect our counting measures basically.
Oh, okay, I see. Yes, thank you.
Okay, thank you. And we still got time for more if anyone else has other questions. Anyone? So, Mustavi, what would be the next step for this? I mean, like this work that have been done. I'm asking this question because I also don't know what so what some of the projects are going to continue on to be.
So next step for this project would be scalability, supporting basically multiple cameras in multiple angles.
Okay.
Also, not just training in the daytime, also training during different conditions. In our training, we just train for the daytime data.
I see.
I think we can improve this by training at nighttime, training the model, which is a bit different. Also training with night vision cameras, because a lot of the cameras these days have the IR blaster with them. And those images come out differently compared to the images you have there with you get with the like daytime cameras basically. So training with different cameras, scalability, supporting multiple cameras, but it is capable of scalability because the systems we use, like Kafka for clustering and all that stuff, it is.
Right. 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 Okay. That it seems we have questions. Okay, Chan Pon.
Okay, Mustavi, you also kind of detect whether the parking spot has been taken, right?
Yes.
My question is, if there are more parking spots to be tracked, okay, how long will it take for you to set that up?
Not long. So basically, it would take a day basically or less. We already have everything in place. We just need to draw the areas we need to track on the parking lot basically. That's it. We have everything in place.
So it can be handled pretty efficiently.
Yeah.
Okay.
Ken, another question.
Yes, I have one more question. Is that if there are two cars that have the same model, same colors, like like when this one car go first and got blocked by another object, and another car with the same color and same model cross it, will it count as like different car or same car?
Different car. Hold on. So yeah, different cars with the same color and same model, right?
Yes.
Yeah, different car. Never as
It's still different car. Like what if it cross an object and they both get blocked and just one car crossed on the other side? How do we know which car it is?
Can you rephrase the question again?
Okay, so for example, I have two cars that always go parallel, and there's an object that block it for a while, like just few seconds, and then only one car crossed to the other side.
Oh, that's where because we keep and log up the IDs, right? And we track the IDs, keep the log of the IDs for a while. So if the car gets blocked, right, we don't immediately lose the track, basically. So we still keep tracking that car that was being blocked, right? So if it appears after being blocked after a while, we still have that car's ID. So it's still being tracked. That's where the Kalman filter comes in.
Ah, okay. I see.
Yeah.
Thank you.